Dear students, now we are going to see the course Signals and System, under that Introduction of Signals and Standard Signals. Upon the study of this Introduction of Signals and Standard Signals, the students can able to understand and the different signal representation and construct complex signals. Introduction. A signal is one that carries the information and defined as a physical quantity that varies with one or more independent variable. Example, music, speech. The signal may depend on one or more independent variable. If a signal depends on only one variable, then it is known as one-dimensional signal. Example, AC power signal, speech signal, ECG signal, etc. When a signal is represented as a function of two or more variables, it is said to be multi-dimensional signal. Example, an image represented as f of x, y. Here x and y represent the horizontal and vertical coordinates. The intensity of image varies at each coordinate. Signal modeling. The representation of signal by a mathematical expression is known as signal modeling. Analog signal. A signal that is defined for every instant of time is known as analog signal. Analog signals are continuous in amplitude and continuous in time. It is denoted by x of t. It is also called as continuous time signal. Example of continuous time signal is a sine wave as shown in figure. Digital signal. The digital signal that are discrete in time and quantized in amplitude is called digital signal. The representation is shown in figure. The basic elementary or the standard representation of continuous time signals. Step signal. For continuous time, step signal is defined as u of t is 1, t greater than or equal to 0 and 0 for t less than 0. And for discrete time signal, u of n is 1 for n greater than or equal to 0 and 0 for n less than 0. The graphical representation of both continuous and discrete time step signal is shown in figure. Ramp signal. For a continuous time, ramp signal is defined as r of t is equal to t for t greater than or equal to 0 and 0 for t less than 0. For discrete time signal, the unit ramp is defined as r of n is equal to n for n greater than or equal to 0 and 0 for n less than 0. Parabolic signal is defined as x of t is equal to t square by 2 for t is greater than or equal to 0 and 0 for t less than 0. Unit pulse signal. Pulse signal is defined as pi of t is 1 for modulus of t is less than or equal to 1 by 2 and 0 otherwise. Impulse signal. The continuous time signal unit impulse signal is defined as del of t equal to 0 for t is not equal to 0 and integral minus infinity to infinity del of t into dt is 1 when t is equal to 0. So impulse signal is defined only at t is equal to 0. Discrete time impulse signal is defined as del of n is 1 for n is equal to 0 and 0 for n is not equal to 0. Sinusoidal signal. For a continuous time, cosinusoidal signal is defined as x of t equal to a cos of omega t plus pi, and the sinusoidal signal is defined as x of t equal to a sin of omega t plus pi. Here omega is equal to 2 pi f is replaced by 1 by t, and omega is angular frequency in radian per second. Capital F is the frequency in cycles per second or hertz. A is amplitude, t is time period in second, pi is phase angle in radians. Cosinusoidal signal. When pi is equal to 0, x of t equal to a cos omega t, that is represented by cosinusoidal signal. Sinusoidal signal. When pi is 0, x of t equal to a sin omega t. The sinusoidal signal is also represented in figure. For discrete time signal, cosinusoidal signal is defined as x of n equal to a cos omega n, and sinusoidal signal is defined as x of n equal to a sin omega n, where omega is equal to 2 pi f, that is also equal to 2 pi by capital N into m. So here omega is the frequency in radians per sample, m is the smallest integer, f is frequency in cycles per sample, capital A is amplitude. Exponential signal. For continuous time exponential, the real exponential is defined as x of t equal to capital A e power at, where a is amplitude, Depending on the value of A, we get DC signal or growing exponential signal or decaying exponential signal. If small a is 0, then we are getting a DC signal. If small a value is greater than 0, then we are getting exponentially growing signal. If small a value is less than 0, then we are getting exponentially decaying signal. Discrete time exponential signal is defined as x of n equal to a power n for n is greater than or equal to 0. Here, if the a value is between 0 to 1, then the discrete time signal is decreasing exponential signal. If the a value is greater than 1, then the discrete time signal is increasing exponential signal. So, if the decaying exponential signal, if the a value is between -1 to 0, then the decaying exponential signal takes alternating sign, and similarly if the a value is less than -1, the growing exponential signal takes alternating sign. For continuous time complex exponential signal, x of t equal to a e power st, where a is amplitude, s is complex variable, that is equal to sigma plus j omega, x of t equal to a e power st. Here s is replaced by sigma plus j omega, that is this term become a into e power sigma t e power j omega t. So a into e power sigma t equal to cos omega t plus j sin omega t. Here sigma is positive, then x of t equal to a e power sigma t cos omega t plus sin omega j sin omega t, where x suffix r of t equal to a e power sigma t cos omega t, and the imaginary part x suffix I of t equal to a e power sigma t sin omega t. The exponential growing and sinusoidal and cosinusoidal signals are shown in figure. When sigma is negative, then x of t equal to a e power minus sigma t cos omega t plus j sin omega t. The real part is a e power minus sigma t cos omega t, and the imaginary part is a e power minus sigma t sin omega t. Here the decaying exponential of cosinusoidal and sinusoidal signal is shown in figure. For discrete time signal, the complex exponential signal is defined as x of n equal to a power n e power j omega naught n. So a power n into cos omega naught n plus j sin omega naught n. The real part of x of n is a power n cos omega naught n, and the imaginary part of x of n is a power n sin omega naught n. The exponentially increasing and decreasing sinusoidal and cosinusoidal signals are shown in figure. Quiz question. The impulse function is denoted by del of t, that is option 2. Thank you for watching.